Yes, it is on. And recording. Okay, so it's my pleasure to introduce Pei from Harvard University. He will speak about TQFT from Coulomb branches. So,
thank you very much for the introduction and the invitation to participate. It's always a great pleasure to discuss and talk with younger students. So, as Thomas has emphasized yesterday, vertex operator algebra has its roots in quantum field theory. And quantum field theories are fascinating objects. So they encode various kinds of information. And you can study them from different perspectives. For example, you can study them by looking at what kind of algebraic structures that they encode. And then you will find some very nice objects, such as VOAs that we have learned a little bit yesterday, and also interesting objects like model tensor categories that I assume that Victor will talk more about next, and many others. But one can also study quantum field theory from another point of view by looking at some geometric structures or identifying some geometric objects. And indeed, for quantum field theories, often they encode some rich geometric structures. There are various moduli spaces that you can associate with quantum field theories. One of them is the Coulomb branch in the title that we'll get to later. So in the two lectures that I will give, we will focus on two types of quantum field theories. They are both conformal, but they live in different dimensions. First, we'll take a look at conformal field theory in 2D and use that to bridge algebras with geometry. And then we will move to higher dimensions. Any questions? We will go to 4 dimensions and see how does quantum field theory in 4 dimensions, how they can be used to relate VOA and model tensor category with some geometric objects associated with this quantum field theory in higher dimensions. So as a quick reminder of what conformal field theory means. So physicists tend to think about conformal field theories as a collection of left-moving modes coupled together with right-moving modes. And if you, if a physicist tell you about some results in CFT, usually what they mean by CFT is this kind of fully fledged CFT that has both left-moving degree of freedom and right-moving degree of freedom. So for simplicity, one can often focus first on only the left moving modes or the right moving modes, and these are sometimes referred to as chiral CFT. And the right moving mode is also chiral, but to make a distinction between left and right, they can be referred to as anti-chiral conformal field theory. And what's interesting about this conformal field theory is that they're actually not a well-defined physical theory or a physical quantum field theory unless you couple that to some degree of freedom. Indeed, here I wrote this tensor products in quotes, and this tensor product is kind of over a theory in higher dimensions, over 3D TQFT. And picture to keep in mind is the following. You can imagine that there is three-dimensional topological quantum field theory in a bulk. So TQFT stands for topological quantum field theory. They are a field theory of a very special kind, and they enjoy a lot of symmetry, and they are invariant under any small deformations. And then the 3D topological quantum field theory can have two-dimensional boundaries. And the chiral and anti-chiral conformal field theories live on the two boundaries of this three-dimensional topological quantum field theory. Another way to say this is that you cannot just study the boundary theory. You have to look at least include some neighborhood to include part of this bulk theory, the theory living in three dimensions. So by 2D CFT here, what I really mean is actually 2D CFT, 2D chiral CFT, coupled to 3D TQFT. And we will use this system in this lecture to relate VOA and model tensor category with some moduli spaces. Any question at this point? So one famous example of this 2D, 3D correspondence is given by WW model on the boundary. So you have already learned a little bit about it yesterday. So as a reminder, WW models is specified by a choice of compact B group. And integer, let's say positive integer, k, known as the level. And then in the bulk, the theory that lives in the bulk can be chosen to be the three-dimensional quantum transaction theory. With gauge group and level k. So there are various ways of defining the theory in the bulk. For example, one can use Any question at this point? So maybe let me say that this lecture is supposed to be very informal. So please feel free to ask as many questions as you would like to, either by just unmute and ask, or by using the chat function. So this quantum transition theory in the book can be defined and studied just by looking at the algebraic data that it encodes. So, but for today, we will take a slightly different perspective, or more physical perspective, by defining this theory using path integral. So the partition function of quantum transition theory and its three manifolds is defined physically as the path integral over the space of all connections of principal tree bundle on the three manifold. And the action is given by k, the level, over 4 pi times the transition form that looks like trace of ADA plus 2 over 3 A wedge A wedge A. So this is how physicists usually talk about and study this transition theory. So in the conformal field theory, one have operators. Some of them are special and known as primary operators. And often, operators in the chiral conformal field theory are not well defined, but instead one should view them as the endpoints of certain line operators in the bulk theory. So these are line operators in the bulk theory that can have some endpoints on the boundary. So one way to see that you cannot just have the boundary theory alone is by observing that these kind of operators sometimes can have monodromies. And that means that correlation functions are actually not exactly well defined, but instead you need to keep track of some additional bulk data to make a correlation function well defined. So in this talk, we'll be focusing on a small part of the data that define, well, that one can get from this system known as the Bolina algebra for G and level K. And they have different kinds of interpretations. One can obtain this algebra by looking at the boundary, or from the view A perspective. Then this algebra can be identified with the fusion rules, or the fusion algebra of primary operators of the WTW model. Or one can study this from the bulk perspective. There, one will identify this algebra as the algebra of line operators. And the relation between them is the connection between them is fairly obvious by looking at this picture. Indeed, if you make the endpoints of this line operator closer and closer, then from the point of view of the boundary theory, you are having some kind of OPE product. But in the bulk theory, what you are doing is that you are fusing two line operators into a single one. And that gives you the algebra of line operators. But the goal of this lecture is to view this algebra from a somewhat more geometric point of view. And geometrically, this algebra is associated with a counting problem. It's controlling a counting, the counting problem of some sort of non-abelian theta functions. Moduli space that I will denote as n flat. This is the moduli space of flat G connections on a Riemann surface sigma. So to make the dependence on G and sigma explicit, I will write it like this. And it turns out that if you do this counting problem for various Riemann surface sigma, you realize that it's controlled by algebra. And that's yet another way to recover this Bolina algebra.
Sorry, G connections or classes of G connections? I mean, up to gauge transformation?
Yeah, exactly. So the moduli space is a modulo gauge transformations. Oh, I should maybe just write it like this. Flat G connection on Riemann surface modulo gauge transformations. This would make it slightly better. Any other questions? And the Bolina algebra is also connected with various interesting objects in physics and in mathematics. So to give you one more interpretation of this algebra, so from quantum geometric point of view, when the algebra can also be realized as either quantum cohomology or quantum K-theory, of Grassmannians, and many more. So as I have mentioned, the connection between 1 and 2 is through this 2D, 3D correspondence that can also be that also has a name, boundary bulk correspondence. Any question?
This is Victor Ostrik. So number 4, it holds only for type A or more generally?
Right. So this interpretation was proposed by Witten, and if one really want to use Grassmannian, one should look at certain UN within the algebra and at some specific level. For UN, there are 2 levels, and it's basically something like k comma k minus n. But actually, this can be slightly generalized to like any g, but times a U1 factor, it turns out. And there, it will be something else that replaces Grassmannians. So it will be quantum cohomology or quantum K theory or some other space. But indeed, for Grassmannians, this is for like UN at some specific level.
Thank you.
No problem. Any other questions? And the connection between 1 or 2 with 4, this is somehow not very obvious if you just study this from pure mathematical point of view. And indeed, this correspondence was first studied by Witten by looking at different phases of quantum field theories. The idea is fairly simple. So phases of quantum field theory is like phases of matter, and sometimes different phases are smoothly connected. We know that in real world, if we look at even phase diagram of water, you have a phase diagram that roughly look like this. So you have ice, water, and water vapor. Maybe I'm messing up with water and water vapor. Yeah. So on this side, it should be temperature. On this side, it should be pressure. Well, indeed, this should be. And then we know that actually, although we often regard the liquid phase and the gas phase as different phases, they're actually smoothly connected. So if you have any quantity that is invariant under small deformation, it's guaranteed to be the same in the water phase and the water vapor phase. And the idea of this correspondence is very analogous. Quantities like the fusion coefficients are naturally integers, and they cannot be changed under small deformations. So, and what Witten did, and subsequently what Karpazin and Willett did in higher dimensions, is by finding a suitable quantum field theory that had different phases. And by connecting them, they managed to connect the interpretation in terms of fusion rule or algebra of line operators with some quantum interpretation in terms of quantum geometry, either using quantum cohomology or quantum K theory. But the focus of the talk today is not about quantum geometry, but instead about geometry of this modular space and flat. And the way to see this is by looking at the Hilbert space of the 3D TQFT, or equivalently, the space of conformal blocks. Of the chiral CFT as a quantization of the classical phase space. So what do I mean by this? So previously, I've written down the action of transaction theory. And it's a quantum theory, but it's kind of obtained by quantizing a classical theory. And for any classical theory, one can ask, what is the classical phase space? And for transaction theory, you will write down an equation of motion that's simply given by Fa equals 0, where F is the connection for the curvature A. So this is the equation of motion. For classical transaction theory. And then this tells you that the classical phase space is indeed just the model space of flat connection. You look at configuration or connections with flat connection and quotient that by gauge symmetry. And this space is naturally symplectic, which is what one should expect from for any classical phase space. And the symplectic form is sometimes referred to as a Thibaut form. Or a Thibaut Goldman form. So, but this is a classical phase space, and for quantum field theory, that is obtained by quantizing the classical phase space, but instead have a Hilbert space. And this Hilbert space is obtained by geometric quantization of the classical phase space and stays in this Hilbert space, then has the interpretation of a certain non-abelian theta functions on this classical phase space. So this is interpretation that we will try to explore further in this lecture. So for us, we'll be interested in look at just first a dimension of this Hilbert space. And to make the dependence on the underlying Riemann surface more explicitly, we will write it like this. And because H is expected to be the Hilbert space of 3D TQFT, this dimension can be identified with a partition function of the 3D TQFT on the Riemann surface and S1. And the reduction of a 3D TQFT will be given by a 2D TQFT. And this 2D TQFT that is obtained by this reduction has a name. It's often referred to as G set G gauged WW model. Recall that for WW model, it's labeled by a choice of a group. And then you can gauge a subgroup of it. That's related to the coset construction that many of you are familiar with for the view A. And but if you gauge the entire G, you are not then you don't have any local degree of freedom left. Instead, you have a theory that looks trivial locally, but there's some kind of global structure to it, and that's exactly what a 2D TQFT is capturing. And 2D TQFTs are particularly simple. The data it encodes is the same as the data for commutative Frobenius algebra. So therefore, for us, if we start with the initial data that is specified by the choice of G and the level K, this will be translated into a commutative Frobenius algebra that is specified by the following data. So here, V is going to be a finite dimensional vector space and will work over the complex numbers. So it's finite dimensional vector space over C, and this is from the point of view of 2D TQFT is the Hilbert space of the 2D TQFT S1. So Z here is for this 2D TQFT. And star here give you products on this space V. Maybe let me write it again like this. And this is what the TQFT would associate to a pair of pens. So for those of you who are familiar with the Atiyah-Segal axiom for TQFT, then you know that this Z can be interpreted as a functor, and then you can apply it on one manifold like S1, or Bourdisms between one manifolds, such as this pair of pens. And what you get is going to be maps between vector spaces. And in this example, it will be exactly a map that looks like this. And further, another piece of data that specifies this commutative Frobenius algebra is a bilinear pairing on V. And this is what the TQFT associates to a cylinder. And lastly, you have a map from C to V specifying the unit of this algebra. And this is what the TQFT would associate to a cap. So it's conversion from the empty set to S1. And for the empty set, the TQFT would associate to that one-dimensional vector space. So you will have a map from C to V. And then you have a bunch of conditions or constraints that is satisfied by all this data. And for example, the product is supposed to be associative and commutative. And has a unit given by the last map. And this bilinear pairing is supposed to be non-degenerate. And it satisfies the following relation. For any A, B, C in V. So this is the data that define for you this commutative Frobenius algebra that capture all the algebraic structure of the 2D TQFT by reducing this three-dimensional TQFT. So let me try to be very concrete. Consider the case that G is SU2. Then dimension of V will be K plus 1. And there is actually a very nice basis denoted as E0, EK through EK. And E lambda, they are in one-to-one correspondence with integrable, irreducible representations of the loop group of SU2 at level K. And lambda can be viewed as elements in the weight lattice of SL2. And in this case, it's identified with the integers. Now the algebra structure is given by the following. You can take two basis vectors labeled by lambda 1 and lambda 2. And then you can expand their products, again in this basis, and you will obtain fusion coefficients denoted as f lambda 1, lambda 2, lambda 3. Let me give their form later. First, I would like to introduce another set of data that so if you consider the inner product between two basis vectors, and you can encode all this data into a symmetric matrix of size k+1 times k+1. In this case, eta will be something very simple. It'll just be delta lambda 1, lambda 2. So all the interesting algebraic structure will be encoded in this fusion coefficients. And they are given by the following. First, so it's either 1 or 0. And it's a 1 if the sum of them is even. And delta lambda 1, lambda 2, lambda 3 is smaller or equal than 0. Here, delta lambda 1, lambda 2, lambda 3 is defined as the maximum of lambda 1 minus lambda 2 minus lambda 3, lambda 2 minus lambda 1 minus lambda 3, and lambda 3 minus lambda 1 minus lambda 2, lambda 1 plus lambda 2 plus lambda 3 minus 2k. So it will be 1 if these two conditions are satisfied. The sum of all lambdas are even, and also this function of lambda 1, lambda 2, lambda 3 is smaller or equal to 0. And you will be, this f is going to be 0 otherwise. So one way to better understand this condition, the condition conceptually, is that this is roughly saying that this triangle with edge length given by lambda 1 over k, lambda 2 over k, and lambda 3 over k fits inside SO3, sorry, SO2. So the first three condition that all three smaller than 0 is obviously the condition that you can form such a triangle. And then this condition tells you that the size of lambda is not supposed to be too large, so that it can fit actually inside the group manifold of SU2. So if you use this, then you can make very explicit the algebra. For example, when k equals to 2, there are going to be 3 basis vectors denoted as E0, E1, E2. And they correspond to 3 finite dimensional representations of SL2, the trivial representation, the fundamental 2-dimensional representation, and the 3-dimensional adjoint representation. And then the algebra is simply given by something like this. 2 times 2 equals to 1 plus 3. This is what you expect, what representations of SU2 or SL2 would behave. But then you will also have 2 times 3 equals to 2. And 3 times 3 equals to 1. So this is, so you get some algebra that looks like the representation ring of SU2, but with some representations removed, very roughly. And one geometric way to encode all this data of the fusion coefficient is by looking at a cube in the space of lambda 1, lambda 2, and lambda 3. And the condition that this function delta is smaller or equal to 0 is saying that the fusion coefficient is only non-zero if you are in the interior or on the boundary of this tetrahedron. Inside or on the boundary of of this tetrahedron. So this algebra, so by making this algebra very explicit, you can do some very concrete computation. For example, you can look at the partition function of this 2D TQFT on a genus 2 Riemann surface. And because the genus 2 Riemann surface can be cut into two pairs of tans facing opposite directions, you will simply have a sum that looks like the following. You have this f, the fusion coefficient squared, with the summation run through lambda 1, lambda 2, and lambda 3. Well, but this is something quite simple because f is either 0 or 1. You can remove this square. And also because f is only non-zero inside, when you are inside on the boundary of this tetrahedron, you are basically counting points or even points inside the tetrahedron. And if you do this, you get something very simple. So it will be the following polynomial in K, where K tells you the size of the edge of this cube. And although there are some rational coefficients, actually this is always an integer. And what is this 1/6? Well, it turns out that this 1/6 can be interpreted in many ways. It happens to be the volume of CP3 with a particular choice of normalization. So if you choose this omega to be the generator of H2 with integer coefficients, then the volume of CP3 is 1/6. It turns out that this is not a coincidence. Also, 1/6 is 1/pi squared times the value of the Riemann zeta function at 2. And this also turned out to be not a coincidence. Well, why CP3 emerged? CP3 is exactly the moduli space of flat connection on a genus 2 Riemann surface. And this omega, with this choice of normalization, is exactly the Atiyah-Bott 2 form. So CP3 is a phase space of the quantum transaction theory with gauge group SU2. And
how
yes.
one can see this?
For this, one way to see this is by really looking at the model space of flat connections. So, and then by identifying this as a character variety of the genus 2 Riemann surface, and literally solve, get a system of equations and identifying that with CP3. So this can be identified with character variety of genus 2 Riemann surface. This pi1 of this can be there's a particular presentation of this pi1 that can be made very explicit. And then you literally get this system of equations, and then you can recover CP3. There are different ways. There's another way of seeing this. I think this is so by a theorem of Narasimhan and Seshadri. I hope I got correctly. This can be identified with the moduli space of GC bundles of holomorphic GC or SL2C bundles of the Riemann surface. And that problem has also been analyzed for this genus 2 case, I think by Newstead. And there it was found that it's indeed CP3. So one thing that you can convince you of is that model space of this type always has H2 being with Z coefficient, being one-dimensional, and it always has dimension equals to 3G minus 3 compact dimensions. So certainly CP3 would fit the bill. But to see that it's really CP3, that require doing some computation and some more careful analysis that I will not do here.
Sorry, is it clear at least why this manifold should be complex?
So the question is that why this is supposed to be complex? So here,
yes,
yeah,
before
it's not
explicit.
right. Right. So here, from this side, it's not completely obvious, but because the theorem of Narasimhan and Seshadri relate that to this moduli space, which is complex, then you know that it's actually equipped with a complex structure.
Thank you. So is it so for all such modular spaces of flat connections?
Sorry, could you say? Could you ask again?
So does this theorem work for any modular space of SU2 flat connections?
Oh, any SU, yeah. So by any you mean any Riemann surface?
Yes.
Yeah, exactly. So and it works more generally, not only for SU2, but for a more general group. And you can also generalize to the cases that the Riemann surface has a marked point, and that corresponds to model space of parabolic bundles. So there are various generalizations, but certainly it's true that the Riemann surface is can be completely general, not necessarily genus 2.
Thank you.
Any questions? Any other questions? So CP3 is going to be the classical phase space, but how to get the quantum Hilbert space from the classical phase space? So as I mentioned, there is a procedure known as geometric quantization. The basic idea is that starting from the classical phase space and flat omega, or in the case of level k times the T-about 2 form. And then, because this space away from some singularities is actually Kähler, the Hilbert space obtained out of quantizing this is expected to be holomorphic sections of certain line bundle at level k, sorry, to the k's power, where this line bundle, in this particular case, is known as, we constantly usually refer to as a determinant line bundle. And it has a property that C1 of this line bundle equals to omega. So here, I have already used the interpretation of M flat as the moduli space of GC bundles. So to be more precise, there is some kind of stability condition that that needs to be included to get a well-defined moduli space. So in the case of CP3, L will be something very simple. It will just be the O1 line bundle over CP3. So the Hilbert space of transforming theory, this genus 2 Riemann surface, will simply be given by the space of holomorphic sections of OK on CP3. And I'm sure that most of you in the audience would immediately know how to find dimension of this space. So this space is going to be generated so this is also the space of homogeneous polynomials in 4 variables. With degree k. So what are homogeneous polynomials at degree 0? Well, that's just the constant function. So in this case, the dimension will equals 1. For k equals 1, dimension equals to 4, with the generator just being, well, x, y, z, w. when k, for example, equal to 2, then you can easily list all homogeneous polynomial in 4 variables with degree 2, and you find that dimension actually equal to 10. For general k, you have exactly this formula: 1/6 k cubed plus k squared plus 11/6 k plus 1. And you can get this formula by either, again, count such homogeneous polynomials by looking at integer points inside the tetrahedron. Or alternatively, you can compute this number by applying index theorem. The index of or homomorphic order characteristic of OK is simply given by this formula. And if you expand this and compute this, you will exactly get this formula. And the leading order to leading order, you will indeed interpret this 1/6 as the integral of e to omega on CP3. So it's not a coincidence that the volume of CP3 rises. So from here, we can go in well, several different directions. Let me first maybe mention that one can easily define this for more general tree. Within the algebra, or more general tree can be obtained in the following way. First, one look at the Cartan of tree, and that T denotes the Lie algebra of T. This is the Cartan subgroup. And then the Coulomb form, or k plus h times the Coulomb form, which is the dual constant number. Give you a map from T to T star, the dual of T. And you can exponentiate to get a map from T to capital T star. And then there is a finite subset of capital T defined as the pre-image of identity of T star. And this is a discrete set inside capital T. And then you can let your V to be functions on regular part of F quotient by the while group W. So W acts on T, and this map chi is also equivariant with respect to W, and 1 is a fixed point of W. So you will have the action of the while group on F. So functions on a finite set is a little bit boring. And in this case, there is a good, well, a nice basis. So that is complete. And they are given by characters that looks like, well, the following. So this is a familiar, well, character formula. It defines functions on T, and of course that can also be used to define functions on regular parts of F. And this is so this is by construction while group invariants. And this turns out to be a complete basis. If you have chosen lambda to be dominant with the condition that products between lambda and theta, where theta is the highest root, to be less or equal in K. And then there's a natural algebra structure because you can multiply functions. And then you further demand that this inner product is given by lambda 1 star, lambda 2 star. Sorry, delta lambda 1, lambda 2 star. So it's non-zero, only one. Lambda 1 and lambda 2 are dual representations. And then you further have a unit that's given by the constant function, or equivalently viewed as the character corresponding to lambda equal to 0. So this is a generalization for general G. And one interesting feature is that here we don't need to choose this particular basis. This is very nice for various applications, but since V is identified with the space of functions on finite set, why not just choose delta functions that is only non-zero on a single point inside this finite set. And this tells us that we can easily diagonalize the fusion rule by using just delta functions. And the change our basis from this character basis to the delta function basis is given by a matrix with matrix elements given by the evaluation of theta on f nu, where f nu is elements inside this finite set. So here, I have used ways also to label elements inside this finite set. This is possible because there is isomorphism between integrable highest weight or in other words, dominance weights that satisfy this condition at level K with this finite set given by sending, maybe let me use nu. To the exponential of nu plus rho dual over k plus h. And this turns out to be related to the modular S matrix. Namely, S lambda mu will be exactly some normalization factor times theta lambda evaluated at f nu. And one can easily fix this normalization by the condition that S times S dagger equal to identity. And so this is a concrete way of seeing a claim by, or fascinating results by Eric Verlinde, that S transformation diagonalizes the fusion rule. So in particular, for SU2, the S matrix would take the following form: 2 over k plus 2 to 1/2 power sine pi lambda plus 1 nu plus 1 over k plus 2. So 2 is a dual constant number for SU2. So a general feature of the S matrix is that it's symmetric. So indeed, you see that this formula is symmetric between lambda and nu. Although this formula is not obviously this side of the right-hand side of this equation is not obviously symmetric under exchange of lambda and nu. And one application of such a concrete formula for S matrix is that this it would enable us to easily compute the partition function of the 2D TQFT. So this stands for the partition function of the 2D TQFT on any genus tree-Riemann surface, because it diagonalizes the fusion rule, and then you can simply cut a genus tree-Riemann surface into a pair of pens. And then since the fusion rule is diagonal, in the end, you only have a single sum over lambda. So you have this formula for the partition function of the 2D TQFT on a genus tree-Riemann surface. And this is known as the Bolina formula. In the case of SU2 and G equals 2, if you take the large K limit, then you can again reproduce the leading coefficients. So recall that the Bolina formula for genus equal to 2 at level K has this form. So by literally taking a large K limit inside this formula, you can recover this 1/6, and there, this 1/6 is identified with 1/pi squared, and value of Riemann zeta function at 2. So this is a fun exercise that I recommend young students here of trying. So perhaps more interesting generalization of the Bolina algebra is achieved by considering replacing G not just by a general group, but instead by a complexified group. So just like Bolina algebra has various interpretations, one can ask for which of the interpretation one can replace G with the complexified GC, and what happens to the other interpretations. Recall that for the first interpretation is in terms of either CFT or VOA. So fusion rules in VOA. Second one is in terms of 3D TQFT. And then in terms of geometric quantization, also modest rate of flat connection, and another one that I didn't talk too much about, quantum cohomology, quantum K theory of certain spaces like Grassmannians. So here, if you look at this list, you realize that some of them indeed can be naturally complexified. For example, before, this is moduli space of G connections on a Riemann surface sigma. Then you can ask, what happens if I replace this with a moduli space of GC connection on the Riemann surface sigma? Just like this space can be related to the moduli space of homomorphic GC bundles or semi-stable GC bundles. This space also has an interesting interpretation as the moduli space of Higgs bundles. And in terms of Coulomb branch. Of certain 4D, four-dimensional conformal field theories. So the third interpretation can be easily complexified. And one can ask what happens for the other interpretations. And what happens for the algebra? Well, it turns out that this space is non-compact, and if you do geometric quantization in a naive way, you get an infinite dimensional space. But fortunately, as we will see in the next lecture, there is going to be certain U1 action with compact fixed point. And one can actually obtain infinite dimensional Hilbert space, but it has also has this U1 action with finite dimensional graded pieces. So the Bolina algebra by doing this, this quantization problem is again controlled by a community Frobenius algebra. And that's a one-dimensional deformation of the Bolina algebra. It's something that I will refer to as the equivariant Bolina algebra. So it's a one-parameter family of a deformation of Bolina algebra. And it also has interpretation in terms of three-dimensional TQFT. So here, for Bolina algebra, the TQFT is transamination theory. With gauge group G. And for the equivariant Bolina algebra, it's related to three-dimensional transamination theory with non-compact gauge group GC. But how about interpretation of this at level of CFT and VOA? Actually, we don't have good understanding of this question. So we understand better the connection with CFT in 4 dimensions, which further encodes some other CFT and VOA. But it's not entirely clear whether this equivariant Bolina algebra is computing dimension of conformal block of some non-rational VOA. This is something that would be interesting to explore. So I will say a little bit more about it later. In terms of this interpretation, instead of looking at quantum comodular Grassmannian, now one should look at equivariant. Quantum K-theory. Of some other modular spaces known as the modular space of vortices. So it's some modular spaces that looks roughly like the total space of the adjoint bundle over Grassmannian, but nonetheless has some interesting global structure that distinguishes itself from just a vector bundle over Grassmannian. So next lecture, I will talk more about what, in general, Coulomb branches of four-dimensional conformal field theory looks like, and what this one parameter deformation of the Bolina formula look like, and then how the two are connected. And I will also focus on a special class of the four-dimensional CFT, and they have some interesting property, and their Coulomb branch actually encodes some information for a certain modular tensor category that is not obvious from the start. So let me end here. So any questions?
I have a question probably to the very beginning. So how you have passed from 3D Chern-Simons theory to 2D topological quantum field theory? You said that you gauging this theory or something like that.
So from three-dimensional Chern-Simons theory to two-dimensional theory, right? That's simply
but there are two-dimensional theory. One is WZV theory, and another one is some topological theory. And I ask about topological one.
Yeah. So the topological one is simply the reduction of the 3D TQFT. So if you have 3D TQFT, you can simply put that on a circle times the two manifolds, right? And that's known as dimensional reduction. So now the 3D TQFT will become a 2D TQFT. And it's an interesting feature that that theory is related to gauging of the original WZW model.
But there is no like physical derivation. Yes, this is just coincidence or what?
There is some sort of physical derivation, but one should notice that it's not the gauging of the chiral WZW model. It's the gauging of actually the full WZW model. So so one can derive from the, for example, the action of Chern-Simons theory, and reduce that on circle to get the action of the gauge WZW model. But this is I think this is a special feature for this WZW Chern-Simons coupled system. If you replace that with something else, it may not be true that it's simply obtained by gauging.
Thank you.
I noticed that I missed an H in here.
Other questions?
I have one. At the end of this first lecture, you consider the simplification of the gauge group from SU2 to SU2C, for example. And I want to ask you, what about the other real forms, for example, SL to R?
Yeah, that's an extremely interesting question. So there one can again use what I'm doing. One can use the interpretation in terms of model space of flat connection. And there you can again find another model space, the model space of GR connections, and that can also be identified to a model space of Higgs bundles. And that's non-compact, but again, it has some kind of U1 action. So geometric quantization of that space again gave you some finite even dimensional Hilbert space, but with finite dimensional weight pieces. So there's also deformation of the Bolina algebra that capture that. So in short, yes, one can consider this problem. So I don't think this has been considered like studied in full generality. So this arrow, this kind of compactification was so we did this with Sergei Bukhov. And then later also with Jon Anderson. And then with Thomas Hausel, we studied like real forms of some specific type, like U1,1, which is real form of GL2C, if I remember correctly. Sorry. Well, I think it's, oh, okay. Yeah, I think it's a real form of GL2C, and also something like SL2R. So it's not too hard to generalize this to more general real forms. I guess the interesting question, well, there are many interesting questions from the point of view of geometry on the model space. It will be interesting to see whether this kind of approach can indeed shed light into the geometry of these model spaces. I hope this answers the question.
And I'm also interested in VOA side.
Oh, what happens for like VOA, like for non-compact real forms? Yeah, I think that's again an extremely interesting question. So at this stage, I don't know much about it. So one can go again to 4 dimensions. There, the story is actually quite interesting. So taking a real forms roughly corresponds to choosing a boundary condition of the 4D theory. And through the work of Galto and others, Galto Casello and others, you know that that kind of system is exactly will exactly give you some kind of a VOA. So by doing that, you expect to get some non-trivial connection with VOA.
Thank you very much.
Other questions? Okay, so there are no questions. Let's thank the speaker, and we'll resume at 8:30 Moscow time. So we have 50 minutes left.
But we can do it earlier. Maybe half an hour will be enough, no?
Well, but probably there are people who are not present here right now, but plan to attend Vitya's talk. So
you
yes.
think?
So it seems we have to follow the schedule.
The schedule, okay. Okay. Mhm.
So we resume at 8:30.
Mhm.
Hmm?
So if there's any remaining questions, I'm more than happy to answer them and to discuss.